Hello, welcome to Notes 8.04. I'm doing your video a little bit different today. I'm going to talk about cross sections. So cross section is the face that is formed when you make a slice through an object. And I want to do a little demonstration today with a few objects that I have made out of Play-Doh. So here are our objects. Okay. And what we're going to do is I have a knife and I'm going to do a few cross sections to each object. All right. This is going to represent a cylinder. Okay. I had kind of formed it around this cylinder here. Okay. Best I could. Again. We have a prism. So cylinder and prism we're going to do first, and then we're going to talk about the cone and the pyramid because those are kind of related as well. Okay. So looking at your cylinder and this triangular prism, okay, we can cross section this across the middle or down the middle, all right? Now I'm going to do a cross section that goes parallel to the base. So again, this cylinder is sitting on the circle. There's a top on up top and then the circle on the bottom. And if I did a cross section through the middle to slice this cylinder, and we open it up, now again, a little bit of error here with the Play-Doh, right? But essentially, that cross-section gives you a circle on either place, okay? I can kind of mush it back together to make my cylinder happen again. So when we do a cross-section through the middle, we're gonna end up with a shape congruent to each base, all right? So if each base is a circle, the cross-section through the middle will also give you a circle. Now if I go perpendicular to the base, so this knife is going straight down through our figure here, what we're going to create, you can see it, is a rectangle. Okay. So when we go parallel to the base, we got a triangle, okay, parallel. When we go perpendicular to the base, straight down the middle, we end up with two rectangles. Okay. So that's for our cylinder. For a triangular prism, so again, this is, think about a slice of pizza, okay? If I take the cheese off the top of the pizza, we're gonna end with this triangle. Now again, best case I could do there, but this should be a triangle, okay? We could slice this many of times, and if we go parallel to the base, you're gonna end up with a bunch of triangle layers, okay? However, if I go perpendicular to the base, straight down the middle, okay? Now this is an equilateral triangle we tried to do here for us. If we go straight down the middle, we end with a couple more rectangles, okay? So again, across at the point, straight down the sides, we end with a two-dimensional rectangle. So again, that was perpendicular to the base, okay, making right angles. When we have a cone, right? So again, I kind of put this pink Play-Doh inside of a cone, or we have a pyramid here, okay? Kind of formed it around this pyramid. Same thing there around the cone. Same case. When we go parallel to the base through the middle, we're just going to cut off a bunch of circles. So if I slice this best I can, well, it's not working so well. There's another way I can slice this. I don't know if you've watched those life hack videos, but sometimes we can use floss to kind of pinch off a layer here, all right? So with that said, we end up with circles, but these two circles are going to be of different sizes, okay? The bottom of this new cone that I just created is a different size than the base, okay? Almost could make a hat out of that. So when you slice parallel to the base and go up toward the point of the cone, you're going to make smaller and smaller circles. So again, this is going parallel to the base. When I go perpendicular to the base, okay, straight down through the middle of my cone here, let's see if I can get it. Okay. Guess what shape we're going to create? With two-dimensional shape. Oh, had a little hole in my Play-Doh there. We're going to have 2 triangles. Okay, so that's the shape that we're looking for. It's a 2-dimensional shape if you slice it straight down the middle like a ninja sword. Okay. So that cone created 2, it's going to be isosceles triangles. So as nice as this is, when I tear off the front here, this triangle should be isosceles, where these 2 diagonals and this base make a nice isosceles triangle. That was a nice perfect cone. Mine's a little lopsided. And last scenario, this pyramid. Again, the base shape here is a square. Okay, so any parallel cut to the base would be smaller and smaller squares as we go up. Okay, and when I go through this pyramid, now I'm going edge to edge, if you can tell here. If I go straight down through, loss is not as big as it. We should end with 2 beautiful triangles. So I'm gonna use my knife and slice through that just a smidge more. There we go. Okay. But we end up with 2 triangles. So that's cross sections, again, perpendicular to the base, coming straight down through the shape, through the middle, or parallel to the base, going up our shape. One other idea that we did want to talk about for today is rotation. Okay. Now here I have, really just part of a folder, okay, a rectangle, okay, and it's attached to a pipe cleaner. And what we want to think about is if that rectangle rotates around, okay, that 2-dimensional shape rotates around, what 3-dimensional shape is it going to create? So again, the corners of this go around in a circle. The base back here go around in a circle, okay? So when you rotate that shape around, you create a cylinder. I don't know if you see it really quick, but you're going to create a cylinder. So again, each corner here kind of rotates around, and you're going to create a cylinder. So the height of this rectangle is the height of your cylinder, and each measure across half of this rectangle, again, the whole rectangle is the way through, would be your radius for that cylinder. Okay, and we had to find the volume of a shape created by a rotating 2-dimensional shape. We would create a cylinder in this case. And here I have a triangle. And if I rotate this triangle around like a flag, okay, you're going to notice, I'm going to do this best as I can here, the end closer to you is rotating around in a circle, okay, and the part to me is kind of staying stationary, the tip of this piece. So when we rotate this around, we're going to form a cone, okay? You can almost think of this as a drill bit, okay? When you go to drill into something, and if I twist it toward you, the end of the drill bit, okay, is pointed, and then it gets wider at the bottom to make a larger hole in an object. And this is a little bit easier to explain in person, but again, if I rotate around the edge of this right triangle, we find a cone is formed. One shape I forgot. Okay. Let's go back to cross sections of this apple, this sphere. Okay. If I cut this apple across the middle here, tip it down the side, what 2-dimensional shape do we form? Some of you are saying it. That's plastic knife is not very easy to cut this apple in half. But if we have a sphere, like many of you know, and you cut a sphere in half, you do create a couple circles. All right. So we today sliced some 3D solids parallel or perpendicular to the base. And we're also going to kind of continue into the notes here momentarily. So looking here at your notes packet, a slice of cake, okay? Again, as you take away that slice of cake, that pie piece which would really be a triangular prism. Okay. You're left over with, it's hard to see here, a square on either side. Cheese, you can slice it across the top. You could slice it down the middle. You're going to create some rectangles. So again, these slices are parallel to the base shape, and you're going to get the same shape as the base shape would be. These slices here, these three pictures, is when you slice perpendicular to the base. We also, in the previous part of your video, had a two-dimensional figure rotated around in a circle, does create a cylinder. So we're going to look more at these rotating figures, and I'm going to sketch them best I can. So if we start with these two-dimensional shapes, this is the idea you have whenever you make a snowflake. Okay, remember you fold your paper a few times and then you unfold it to have certain pieces. And I also have these party decorations I'm going to use to try to explain. So this here is just a big triangle. Okay? And when I open it around in a circle, okay, it's going to end up creating me this cone. Okay? It's actually two cones, the bottom part of the cone and then this whole top part of the cone. So when we're talking about rotating a two-dimensional figure, we're taking this two-dimensional figure and we're spinning it around in a circle to make something a little bit more three-dimensional. So again, if you do take a triangle, this bottom part, we would rotate around in a circle. Maybe reflect this over. You might be able to see the cone that is formed. If we took a rectangle and we rotate the corner all the way around that center of rotation, same thing with the base. We're going to end with a cylinder. As best as I can sketch it here. We take a half a circle and we rotate it around. Again, I'm going to reflect it over first. It draws reflection. I'm just going to draw myself a little semicircle around the middle. We're going to create a sphere. Here we have a rectangle on top of a triangle or a trapezoid. Now the top part, I reflect that across, and then the bottom part reflected across gives me almost like a spaceship. Okay, so it's that cone on top with the cylinder formed underneath it. So we're going to say this is a cone and cylinder. Anyone know what this last shape is? So again, I like to reflect over first. So I took that shape and reflected over my M. Now this point to here rotates around in a circle. This point to here rotates around in a circle. What we're thinking of here is a toilet paper tube. I don't know how well I sketched it, but that rectangle is going to go all the way around and have a donut out in the middle. So there we have a toilet paper tube. Okay. So I'm going to say toilet paper. Silly as it sounds. Exercise 2 is actually taking some dimensions with this idea of rotating a two-dimensional figure and finding their volume. So looking at number 2, a 3D solid is formed by rotating a rectangle, like shown here, about a vertical line. The dimensions of the rectangle are given. Find the exact volume. So this means in terms of pi, okay, of the solid formed by its rotation. And I believe this little box kind of in the wrong spot right here. So our volume is going to equal pi r squared h. And again, as I rotate around, That 3 is going to be our radius, and this 5 is the height. So we're going to take pi times 3 squared times the height of 5 will become 9 times 5 is going to be 45 pi. And didn't tell us what the units were, just be cubic units. So by taking that two-dimensional figure, identifying what shape you're formed, again, we form a cylinder, we can find the exact volume of that cylinder. Density is a topic we're going to kind of bump over to the next page. So density equals mass divided by volume. Well, volume we've been looking at. Mass is a weight, okay? So a shipping container is in the shape of a rectangular prism, has a length of 12 feet, width of 8.5, and a height of 4. So if we draw a rectangular prism, I draw a rectangle. Off to each edge, I kind of draw a diagonal to make a rectangular prism. The base is 12 by 8.5. The height is 4. The container completely filled with contents that weigh, on average, 2.5 pounds per cubic foot. What is the weight in pounds of this container? So whatever is filling this container is about 1/4 of a pound per cubic foot. So what we're going to do is find the volume first. So volume equals the length times the width times the height. So our 12 by 8.5 by 4 are our 3 dimensions we can multiply together. 12 times 8.5 times 4 gives us 408 feet cubed. That's our volume. Now, the container is completely filled with contents that weigh, on average, 0.25 pounds per cubic foot. So what we're going to do is we're going to take our feet cubed over 1 and multiply by 0.25 pounds per 1 foot cubed. So I take this statement and I make it a ratio. How many pounds over how many cubic feet? So when I multiply these two things together, our cubic feet units cancel each other out. Anything over itself is 1. And we're left with our calculation in pounds. So 408 times 1/4 of a pound per foot cubed will leave us with 102 pounds of content that are in that case. Exercise 4. A machinist creates a solid steel part for a wind turbine. Okay? So we have turbines that rotate. These 3 pieces rotate around to create wind power, wind energy. The part has a volume of 1,015 cubic centimeters. Steel can be purchased for 29 cents per kilogram and has a density of 7.5 grams per cubic centimeter. So cubic centimeter, grams, okay, and kilograms. We have a bunch of units kind of going on in here. If the machinist makes 500 of these parts, what's the cost of the steel to the nearest seller? So a couple of unit measures we were given. The volume is 1,015 cubic centimeters. The price that we have is 29 cents per kilogram. And our density is 7.95 grams per centimeter cubed. So we're going to go back and we're going to use that density equals mass over volume formula. So density equals mass divided by volume. What we're asking for is, for 500 of these parts, what's the cost of the steel? So we have to decide how much steel we have, and then the cost is per kilogram. So we need to kind of get our calculation into grams at least. So our density is 7.95 equals the mass over our volume we know is 1,015. So like normal, we're going to cross multiply here. So 1,015 times 7.95 is going to give us that the mass, or the weight, is 8,069.25 grams. Now again, the reason that it's in grams is because this is grams per centimeter cubed and centimeter cubed. So those canceled itself out and we were left over with gram measurement. Our 29 cents is per kilogram. Now, 1 kilogram equals 1,000 grams. So we need a smaller unit compared to the large unit we have. So to change grams into kilograms, we're going to divide by 1,000. And that's just going to move your decimal over a couple spots, 3 spots. So our conversion here is 8.06925 kilograms. And if our price of 29 cents per kilogram, we're going to multiply here by 29 cents, we get approximately $2.34 per part. And we need 500 of them. So our final answer is $2.34 times 500 will give us a grand total, I come back to my calculator screen here, of about $1,170.04. So we amount money times 500 parts, and we get our final answer. Now that was kind of a lot of this to unpack. Okay? Again, following back through the question, we were given a volume. We were given a price per kilogram, and we were given a density. So density equals mass over volume. We were trying to find how much weight we had because this cost is per kilogram, or its mass. Exercise 5 is going to be an extra credit question if you'd like to try it as part of your assignment today. Again, same kind of idea. We have 500 bricks. Each brick has a dimension to it. The density is given here. Okay. The maximum capacity is in kilograms. You're deciding, can a trailer hold it, and justify your answers. We're looking for some kind of explanation there with that. So if you'd like to try exercise 5 as extra credit, you can. And your classwork for today is 804. Okay. Hemispherical tank. Again, volume of your hemisphere was that 2/3 pi r to the third power. Oops, sorry, I got off the screen there. Exercise 2, try what you can to describe each of these figures that get rotated around. Again, my hint here is to reflect it first and then kind of draw in the base. Exercise 2 is in the coordinate grid, so it's kind of mixing our volume unit and our coordinate geometry. Find the volume of the cone in terms of pi formed by rotating around side AB. So this would be your line of reflection here. So you're going to reflect your triangle down, counting the boxes, 1, 2, 3, 1, 2, 3. And understanding that you formed a cone in this fashion. So try what you can there. There's 2 parts to this. So they wanted you to find the cone in terms of pi by going around AB, but then also, if you think about that cone or that triangle here, what would be the volume if we rotated it around that y-axis? It's going to be a much wider cone. So try both parts. Again, it's to make you think. Number 3, if you see this shape, it's a prism, and then there's a hole drilled through the center. Okay, so if you had a piece of wood and we kind of stuck a hole down through the center, to be honest, it's almost like the idea of my paperclip case here. Notice the hole here through the middle. If I was trying to drill straight through here and decide how much space was left over, that's what we're trying to find. So you're going to find the volume of the prism first, You're going to subtract the volume of that cylinder to be helpful. Exercises 4 and 5, again, more conversion kind of questions. There's a reference sheet conversion on your page about 1 pound and gallons. We want you to try what you can. All right. Email me with some questions, but again, these I want you to read, internalize, find some resources to help yourself answer them.